Okay, so first a little bit about me. So my tagline is that I like to solve hard problems. Let's hold my beer. These are my social links, and I'm currently working as an independent DevOps consultant. So you can find me like in random places and all. And okay, so the disclaimer, a quick disclaimer that DevOps is like a loaded term. Everybody's trying to utilize it for their own ends. We're generally going to sidestep that. We have a complex task to deal with anyway, so we're not going to be nitpicky about this is DevOps, this isn't DevOps, and so forth. We have a beast to tame, so to speak. So we're going to have a two-part lecture, if time permits. So the first thing we're going to talk about is a protocol called DICOM. So it's one of the two major healthcare protocols. The other one is called HL7. And the interesting thing about DICOM is, well, you're not going to deal with DICOM unless you're in the very small healthcare market. You're never going to see DICOM. At least I never heard of it until I started doing healthcare. But it serves like a great example of onboarding a new protocol. You suddenly got into a company, and then they're doing things somewhat differently. So how do you handle such a bomb being left at your desk? And the other thing we're going to talk about is regulations. Regulations is the other bomb that they're leaving next to your desk, is how to deal with all these papers that are being lumped on your table. And by the way, that also works for DICOM because the standard is over 1,000 pages. It's designed by committee. It's pretty much horrible. But again, even if you're not doing HIPAA or other respective regulations, as long as you're in a regulatory environment, that might be, interesting for you.
HIPAA is not as HIPAA as it sounds.
No, most definitely not. Ching. Okay, so like I said, the motivation of doing something like DICOM is learning how to handle a non-HTTP protocol. And the more like the newer age, HTTP is used for everything. The internet used to be full of random protocols, from a protocol for character generation, that just tell nothing to a port, just throw random characters at you. We're kind of consolidated into a few leading protocols. The internet is less rich in that sense, at least, from what it used to be. So here's our game plan. First, we're going to understand what is this DICOM thing, what's it's used for, why does it exist at all, maybe even understand some of its philosophy, a bit of the basics on its philosophy. Next thing we're going to do, we're going to scope its usage in the system. It's probably not going to be, or at least if we can make it as pervasive or totally inclusive, let's see where exactly it fits and try to stick with that as much as possible. And now, after we've done that, we're going to analyze some of its key features and see how if they're useful for us, if they hamper our goals, and so forth, and then see how we can realize them. Okay, let's get started. So DICOM stands for Digital Imaging and Communication in Medicine. It's not just a wire protocol, by the way, it's also a serialization standard. You have DICOM files. It sets exactly what's written in the file. And it's designed by a body called NEMA, which is a national, something of the National Electronics Manufacturers Association. The committee that designed this protocol, they're doing embedded machines. They're doing the CTs, the X-rays, the ultrasounds. It's also there's the industry term for that. It's called a modality. And they have a design philosophy which says be conservative with what you send and liberal with what you accept. That's basically, that's an adage from the old times of the internet, which helped foster interworking. Because unless you have that design philosophy, it's very hard for devices to work together with each other. And even so, you get lots and lots of things that don't work together as they're expected. So that was trying to save the day. And let's say that it helped. It would have been much worse without it, but it's not a silver bullet by far. So, and like I said, it's also, since it's a very specialized protocol, you don't see many implementations. If in the keynote we saw this like huge roadmap of all the software that you can use, in DICOM, I think when it comes to SDKs, you have a grand total of maybe 7 or 8 useful active projects and maybe 1 or 2 daemons. So it's a problem. We have, and that's what the next slide is about. Few implementation means trouble. Because when I have a challenge, I have a lot less stuff to pick from. And I'm going to have to make choices that I don't like and see if I can work around them. Or at least that's what seems like. And otherwise, we'd also have to reinvent the wheel, which is something everybody hates, especially when it comes to the DevOps culture. You don't reinvent the wheel. You don't deploy your own hardware if you don't have to. You go to the cloud. You don't create your own toolchain from scratch. You use CI servers and so forth. We're going to have to do some things, well, hopefully not from scratch at all. But at least we'll have to do some legwork. And also, when it comes to that, the auxiliary components that we're used to are generally missing as well. There's no load balancing, monitoring, utility scripts. It's mostly all missing from our environment. Again, for the exact same reasons. OK, so scoping. What are we going to do with this DICOM? DICOM is the protocol that the CT is using. So hopefully, or what we plan to do is just use this DICOM to ship it into our cloud, and then not see the DICOM wire protocol, hopefully, because we don't like it. But once we've stored the DICOM files in S3, we'll probably start to use more sane protocols as permits. But when it comes to the serialization format, we're actually bound by two equally bad choices. Either we can deserialize DICOM, and then the errors would propagate through our stack, or we can deserialize every time we need it to save the DICOM serialized format, and then still errors would propagate through our stack, but in a different way. So we're stuck with that. It's a complex protocol, and even if we deserialize it, it's probably not going to help us much. OK, the protocol is binary. It's more like a semi-binary. You can find some text in it, and it overlays the full OSI model over TCP/IP. Now, if any of you remember or studied computer theory, OSI is like the full 7-layer model with a presentation layer. Now, in biology, there's a nice term for that. They call it a living fossil. It's something whose only neighbors are identified as fossils. Now, this protocol says, I'm compliant with OSI, but all the other OSI protocols are just totally gone. So it's kind of stupid to have that compliance statement by now. So like I said, it's more like a fossil. And it's strictly regulated also. There are enumerators for everything. They are reserved. You have to set them. You have to set them in very specific ways. Pretty annoying. But or at least seemingly, we don't have to care much for that because, well, from the DevOps perspective, we need to make it scalable, we need to make it secure, and we need to make it work. So maybe we can forgo much of that and have stuff work. So let's see features that we care about. Now, these next four slides are going to be a distillation of hundreds of pages. So even though it's might be a bit hard to keep up with, that's the best I could do, I guess. OK, the terminology for client and server, there's one called SCU, which is basically the client, and SCP is the server, and the client controls the connection. The client is the one making the requests, and the server answers. So it's like a uniplex in that the server can't initiate requests on its own behalf, only in certain conditions which are not part of our scenario, basically. And the commands can be made asynchronous. There is support in the protocol for asynchronous operations, which is important because we don't want to have to do all the ping pong. Again, send the request. Hopefully, you can still send another while you're waiting for the reply. And but it's optional. It's negotiated during the connection creation. That's what the standard says. And OK, the command set is try to maybe rush through that. We're not going to use the N commands. These are the commands. There's associate, release the association, abort the association, which is the only command that the server can still issue. And let's say the vocabulary is very simple. You can send a store command. I want to store a slice or a single image. I want to find an image. I want to move an image between two devices. I want to get an image, and there's an echo. There's still a built-in echo service. And the data may be fragmented over messages. And all messages have unique IDs and are all acknowledged. Even if it's asynchronous, there must still be acknowledgement. There's no multiple acknowledgements. it doesn't look as so efficient, but being asynchronous, it might still be good. We can pipeline when multiplexing if negotiated during the connection. So, and since we're dealing with something called studies. That is, we're dealing with series of images. You don't just send a single CT image, you usually send a series of them. They don't come as single images, for the most part. You want to see something from another angle, the CT machine goes like this, and then it just gives slice, 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 and then you get a good view of what's happening. And another observation is that if we keep the long-term established connections, we have to plan our load balancing more carefully. We have to look at the connections as they build up, because when there's an active connection, if we still go with this way, it might just burst into start sending us thousands of images. But that all leads us to very, okay, actually, oh, here it is. Sorry, I missed that one. So actually, that leads us towards connection-managed load balancing. We're going to keep connection counts, and hopefully that would help us balance the load. If the load balancing uses number of connections, we're probably not going to blast servers in an uneven way, or at least hopefully. That's the best we can do. And another observation is that connection establishment takes a much longer time now, because you have to establish a TCP connection, and then there's another OSI layer that makes another round trip. It says A associate, and then A associate accept. We don't like this connection creation. It's slow, and especially if we're going to go to the cloud, it might be even slower. So we try to avoid that, but luckily we have this C echo thing, so we can keep a connection alive for as much as we want to. Another thing that we can't do is if a node asks for another ACSE name, actually we have a whole set of new namings that are from the OSI presentation layer, so we can't multiplex that on a single connection. We have to create a new connection whenever anyone asks for a different node. And there's a lot of, it's a bit hard to follow, but I'll try to ping us back to where these become relevant. Just a quick recap about what we need the load balancer to do for us. That's something that we take for granted with HTTP, but now we have to make a tally of it and see if we can fulfill it somehow. So first, and obviously, we need to balance a load. We want to have several front ends and not have excess load hit one, and while the other one goes idle. Question?
The client is the machine, or the client is...
The client is the modality, it's the CT machine. Hopefully, in this design, what we're trying to do is that the CT scanner is going to ship the images directly to our cloud. And let's see if we can do that. Let's see if the protocol even allows that to be done in an efficient way. And we're going to have to do some load balancing, obviously, right? And another thing that load balancer does is that it has to detect instance failure, which is trivial with HTTP. There are error codes and so forth. But no load balancer currently understands the DICOM error situations. So we're going to have to retrofit that somehow. Another thing that load balancer should do, and maybe it's somewhat more optional with HTTP, it's good citizenry, but in our system it's a bit more than that, and we have to reflect a safe error condition. If all the nodes are out, we're going to want to have a sane reply that the other side of the system, the client, can efficiently reflect to the operator. If something's going wrong in a medical process, we need to be a lot more vigilant about it than just leave the connection hanging. And that's another thing that we're going to retrofit. Now, most load balancers are just going to throw, with HTTP, they're going to throw a 504, and it's pretty good. And even if they don't, it's not so bad, at least for user-facing. But even for APIs, yeah, we want them to throw a safe error condition. So we have to do that too. And another thing that we do with load balancers occasionally is that we kind of maul the behavior of the client. If the client is not behaving like we want, maybe you can add more headers, modify the headers, keep connections alive, and so forth. We're going to hopefully want to do some of that with our load balancer. And also, another thing is that we want to handle or offload encryption and authentication. Preferably, even more so when it comes to our service, because we don't know how the DICOM daemon is going to handle it, and we're more well-versed with load balancers than this DICOM daemon or so. So that would be very nice for us, and let's see if we can realize all of that. And now that we've mentioned security, let's talk about how we can secure DICOM. So DICOM actually has some TLS support in its standard. Now, some people don't use TLS and they use IPsec VPNs, and we'll dedicate a slide for that, unfortunately. And there's actually authentication built into the protocol. It supports user password model, Kerberos, and SAML. That's nice. And there's even support for digital signatures. That's pretty nice of them. That seems useful. We can build something with that. And OK, but when it comes to TLS as part of the DICOM standard, it's specified in a brain-damaged way. You get to pick from 3 profiles, one which has no encryption, one which has triple DES encryption, and one that has AES encryption. So that's a bit dated and a bit brain damaged, but still viable by modern standards. I mean, triple DES is still considered mostly safe, and TLS1 with AES is considered safe. There's just a thing that says their entity authentication is optional. That doesn't seem so secure. That's starting to give us a bit of a shiver, but we're still good. I think we're still good. It's OK, here we go. We selected the least connections load balancer. We are detecting failed instances with a C echo. If it doesn't return a C echo, we're probably good. And we can even do an associate rejection as part of the association attempt, and it's our equivalent of a 504. And we can do the TLS termination and identification with certificates. And this is pretty much where we can get without re-implementing DICOM or bolting it into something like NV or C code for AJ proxy. It looks good. Things are looking good for us. It looks like we can achieve our stated goals. And if you go to GitHub, there's something I whipped out quickly with AJ proxy and Lua, and it's working. It does all that I've talked about, and ACSC is simple enough to keep it sane with Lua without security risks, buffer overflows, and it looks like we're good. But here comes the but, DICOM in the Wild West. So the first thing when we try to deploy such a thing is that turns out the modalities just don't support any auth method. They just don't support it. Today's magic sentence, when it comes to the DICOM conformance of these modalities, this product does not conform to any defined DICOM security profiles. It is assumed that the product is used within a secure environment. That's a shame. That's a shame. So we have to do all this security in another way. So it turns out it's not too strong with security. But hey, that means, unfortunately, that none of the TLS profiles are supported by the modalities. This is much, much worse for us. And today's magic sentence is still, this product does not conform to any known DICOM security profiles. We are somewhat screwed here because we have to revert to IPsec VPNs. Offside. Why IPsec VPN is a bad idea? It's not a bad idea. It's a horrible idea. Now, IPsec, if you're familiar with that, it's going to ring a familiar chime. It's a cumbersome protocol with lots of options, aka rope to hang yourself with. You do a phase 1 negotiation, and after phase 1 negotiation, your addressing changes, and then you do a phase 2 negotiation, and if it doesn't match, you get a random error that's probably cryptic because I couldn't decrypt for whatever reason. And it's pretty bad. Like I said, expect long debugging sessions and staff your support accordingly. Now, what's even worse with this scenario, it's not just IPsec. It's the fact that we have to support arbitrary IPsec devices. One hospital is going to have Checkpoint. The other is going to have Fortinet. The other is going to have God knows what, a Cisco. That does not look good for us at all. But if we have to chew, we're going to have to bite it. And it's also not so good for failover, to add insult to injury. So, but yeah, that's OK. We still know what we're doing. Sort of. turns out that the modality tends to drop images as part of the series. Some of them it just doesn't send at all. That sucks. And it's something that the industry knows, and it's learned to somehow cope. And if you remember, is the cfind command. So basically what you usually do is if you detect a lost frame, then you issue a cfind to fetch it from whatever it is, hopefully. That's very bad for our design. It means that actually, yeah, our front ends are now going to have to issue commands to the modality or to the PAC server, another component which stores images for reference. It totally threw our design off, off the course. And we're going to have to now devise a network topology where the front end can make and issue requests into the hospital. So that's going to be challenging. But no, actually, it's not going to be challenging at all. You know why? Because cfind means that we have to initiate a connection from our side, but it's impossible due to security considerations. No hospital is ever going to let you issue DICOM commands into their infrastructure. So what that means is that we now have to design an in-premise equipment. It's maybe not so bad, but to be honest, why didn't we opt for, no, not yet. We're going to have a slide about why we didn't, let's say intuitively, we tried not to have an in-premise box in the hospital. And we're going to have a slide about that. And it's tempting to start jumping around it, but yeah. So, and here's the thing, now that we're designing this in-premise box, it turns out that our favorite open source DICOM router does not support multiplexing, which is very, very, very bad for performance. We're not going to hit our performance mark this way. As you remember, multiplexing was an optional feature. And the DICOM router that we have two to make a selection of, and both exhibit this behavior, they do not multiplex. Actually, there's a good reason why they don't, because they can change the ACSC names during their routers. They need to change the ACSC names. So it's somewhat silly to try to hold a connection pool when your name can vary arbitrarily. You're going to hold possibly thousands of connections for no good reason. But what it does allow us to do is have multiple connections. I'm sending one chunk at a time, yeah, but I'm going to do it 60 or 32 connections attempts in parallel, which is sorts of fine. It would have been fine, but the problem is that if you put too little of them, your performance suffers really bad. Again, remember the connection establishment. Now connection establishment comes to bite us. And if you put too much, then connections stall, and then you get a timeout. And then you have to recover from a timeout, which the router apparently doesn't do so efficiently. OK, and what? Already? Wow. OK, I'm going to have to wrap up with DICOM. So and the last insult to injury is that we can't use client-side certificates in a hospital. They have DLP protection, which does man in the middle against your or their TLS connections. So we can't even deploy that. So we don't even have a good way to authenticate. And so, wow, OK. And just another thing is that HTTP would have done quite a bit, little to help us avoid with the problems that we'd have to still have the on-site presence because of the unreliability of the devices. But I'm going to have to rush a bit. I'm terribly sorry about that. We talked about why intuitively a zero footprint installation would have been so much better, because it's, well, now that we've gotten to realize how bad hospitals are, it's going to be a management hell. They're not going to give us access to anything and so forth. So I'm sorry for rushing it. So, but basically the thing is that now our DevOps transformation is more of a people's problem. We need to see what the hospital can give us, ways to manage this atrocity somehow, and to match our deployment insight and get some manageability into it. And this is extremely hard to genericize because every hospital is going to be different, and you have to stick with the product guys or the professional sales engagement guys to make sure that you get what is needed to have a sane architecture and have a say in it and do it. IPsec rules. IPsec is a problem. Actually, now that we have a few minutes, I'm just gonna say something real quick about that one, because that I did actually find in one of the specifications that the modality did support TLS. It was like a discovery of the year. There is TLS support. And then I said, okay, but it was a specific firmware. So I sent an email to the vendor, said, hey, why does that firmware have TLS and none of the other firmwares have TLS? And then the reply was very nice. Said, thank you for your inquiry. We didn't even realize we had a TLS supporting firmware. This was due to some government agency that insisted on it, and it's never going to see the light of day in any other place. By the way, if that makes you feel more safe with regards to your hospital data, that's pretty much the point. Maybe if, now hopefully, yeah, in our ideal architecture, the device would have been able to talk securely and efficiently to the cloud. We're just so far from there. And the resolution, at least currently, is not even technological. It's about people, it's about procedures, it's about access. I mean, technologically, we could see the DICOM sufficed. It was a mess, but it was sufficient. But the problem comes from another area entirely. And that's, again, what to talk about culture and people. That's where resolution of such issues comes from. Okay, thank you very much.